Hello, my name is Luca Soldaini. I use pronouns he, him, and I'm an applied scientist at Amazon Alexa. Today I'm going to present a joint work with my collaborator, Alessandro Moschitti, titled The Cascade Transformer, an application for efficient answer sentence selection. Before we get started, let me give you an overview of this work. What I'm going to present is the Cascade Transformer, a technique to turn a transformer model into a cascade of ranker for faster inference. The reason why we're interested in this model is that previous works have shown that transformers are really good at ranking problems, but they are slow when having to rank hundreds of candidates. The way we achieve faster inference is that we use intermediate representation of a transformer model to drop unlikely candidates from mini batches. Our experiments showed that we can reduce computation by 37% with almost no impact on accuracy on two English QA datasets. So let's get started. To iterate a little bit more on the motivation for this work, previous research has shown that transformer models are really good at modeling ranking problems, especially when we have to model interaction between queries and candidates. This is the case, for example, in information retrieval, as well as in question answering. However, due to their complexity, transformer models are slow at processing many hundreds or thousands of candidates. There's actually not much research on this topic. This is because many academic datasets either have very few datasets or use simpler algorithms, such as a ranking model, to obtain an initial ranking on the candidates and then only use a select subset of candidates to be processed with a transformer model. However, we were interested to see if we could improve overall transformer throughput without using any of these alternative modeling techniques. So let's start with a little bit of review of how transformer models are used for ranking. In this case, I'm showing an example where I want to rank 3 question answer candidates. And I'm using a contextual language model based on transformer to obtain contextual representations for these 3 candidates. And then I'm using a trained feed-forward network with a softmax layer to obtain probability scores on these candidates. And then an argmax operation can be used to select the candidates with the highest predicted probability. So why are transformers expensive for ranking problems? Well, as I mentioned before, transformer models are complex and have high memory requirements, which limits the batch size, the number of candidates we can pass at each time to the transformers. This is not a problem if we only have few candidates, but if we have hundreds or thousands of candidates, then we have to split these candidate sets in smaller batches that we can pass one at a time in the model, which is slow. So this is how a traditional transformer model is used to make prediction in a batch. We call this model a monolithic model. It takes a fixed set of candidates as input and produces probability for these candidates. If you want to speed up this model, a common modeling technique is to create 2 smaller models. The first one is really fast and can work with a large batch size. We use this first model to make some prediction. We discard prediction with low confidence, and then we use the second, larger model to make our final prediction on a smaller subset of candidates, and then select the best candidate. The problem of this sequential approach is that in order to maintain the requirements in terms of accelerator capacity that we have, Model 1 and Model 2 have both to be smaller than the original monolithic model. What we're proposing here with the Cascade Transformer instead is a model that has the same expressiveness of a monolithic model, but that can drop candidates as computation progresses through it. So it can have a large initial batch size, but it be not more expensive than a monolithic transformer model. So let's look at how a Cascade Transformer works in practice. Here I have the same example that I've shown you before. And in particular, we're going to look at how Cascade Transformer model works between 2 adjacent layers. Now we are using the lower layer row here to produce hidden representation for the 3 input sequence. And then we use a train partial classifier on this input sequence to obtain an initial scoring of our candidates. Then candidates with low score can be dropped from the batch, and only the candidates with high scores are passed to the subsequent transformer layers. So each layer, in this case after raw, receives a lower number of candidates. A smaller batch has to process a smaller batch than what the initial layers of the transformer have to process. Then we proceed as with any other candidates. We obtain hidden representation for these candidates, pass them through a softmax, obtain a probability score for each of these candidates, and then pick the one with the highest score. In fact, we can use this technique to place many partial classifiers that can help us reduce the size of the batch as computation progresses through a transformer. In our experiment in particular, we use 4 partial classifiers, and we use only 4 so that there is enough spacing between them for the self-attention mechanism to realign. And we start using partial classifier only after the 4th transformer layer, because we find in our experiments that lower layers not capture as much semantic information than higher layers, so results in worse performance. And this has been confirmed in other works in the literature. You might notice that this approach is similar to diagnostic classifier, but the function of our partial classifiers is very different. We're not interested in assessing the performance of the model and try to understand how the model makes a decision, but instead we use this partial classifier to increase throughput. To train this partial classifier is very easy. We train all of them concurrently. For each mini batch in our training set, we pick one of this partial classifier at random, use it to make prediction, calculate the loss, and backpropagate said loss to the input layer. Inference is equally easy. Assuming that each batch that goes to the classifier contains candidates from the same set, at each of the partial classifier, we drop the fixed ratio alpha of candidates. So where a monolithic transformer here has the same batch size throughout its computation, which results in a number of transformer operation equals to 1200, if we assume a batch size of 100, our Cascade Transformer works a little bit differently. For the first few layers, we work with the same batch size, but then we use the first partial classifier to throw away 30% of our candidates, resulting to a batch size of only 70. Then the second classifier can be used to further reduce the batch size to 49. After using the third one, the batch size goes down to 35, and the final layers only receive a batch size of 25, which is a quarter of the initial batch size. And what this results in is a much lower number of transformer operations. So 758 instead of than 1200, which equals to a 37% reduction in cost per batch as expressed in terms of transformer operation. Now for the experimental setup, we evaluate our approach on 4 datasets. 2 of them are well-known answer sentence selection datasets for question answering, WikiQA and TrackQA. These are well-known in the literature, but unfortunately have very few samples. We also use 2 other datasets that have hundreds of candidates. One of them in ASNQ, which is a dataset introduced by Garg and others that has been derived from the Google NQ dataset. And the second one is an internal dataset we call GPD. We use a combination of high precision metric as well as overall metric that are designed to assess the overall performance of our system. And as baseline, we use a state-of-the-art 12-layer monolithic transformer model. This is a tandem model introduced by Garg and others, as well as a sequential ranker built with 5 transformer models that are independently trained. And these 5 transformer models that we use have 4, 6, 8, 10, and 12 layers. So I'm going to present a subset of the research question we study in the paper. For more thorough analysis, I will encourage you to read our paper. So for the first research question, we were interested in examining whether this Cascade Transformer is better or worse than a traditional monolithic transformer. And to do so, we use the WikiQA and TrackQA dataset, and we study the performance of our model when no dropout is used. And what we found here is that our Cascade Transformer model, when no dropout use, improves over state-of-the-art question answering models. So we outperform our previous best state-of-the-art, which is Standa-based. Interesting also, our training strategy for this Cascade Transformer is also able to produce very competitive smaller transformer model with 10, 8, and 6 layers, which suggests that the training setup that we have for the Cascade Transformer model executes some sort of distillation and is able to produce this smaller, but yet very efficient classifiers. For our second research question, we looked at what's the speed up of this Cascade Transformer model compared to traditional monolithic transformers. And I'm going to present here the results in the SNQ dataset. Again, our paper includes results on GDP on the other dataset as well. On this dataset, we see that when no dropout is used, we see the same trend as with the previous dataset. The performance between our Cascade Transformer and the best state-of-the-art are very similar. We actually outperform the state-of-the-art a little bit. When a little bit of dropout is applied, when we discard 30% of candidates at each partial classifier, we see a small performance drop in the performance of our Cascade model, but with a high increase in efficiency of our model. Our model here loses less than 1 point in MAP, but it's has a 37% lower cost per batch compared to the state-of-the-art. And we achieve similar performance as a sequential re-ranker, but we are much, much cheaper to execute. A sequential ranker here costs 1.5 times the cost of the baseline. When we use a larger value of alpha, we see a larger performance drop compared to the state-of-the-art, but this performance drop is really gradual, which is good because as we increase alpha, we can achieve a much larger reduction in cost per batch. And for a full study of the behavior of this alpha parameter, I suggest you to look again at our manuscript for more information. So to recap, I've discussed the need of sequential re-ranking for problems when many candidates need to be scored with a transformer model. I introduced a Cascade Transformer, a variant of the transformer that improves inference throughput. And these variants use intermediate classifiers at different encoding stages of this transformer to prune candidates in a batch. The Cascade Transformer achieves a comparable better performance than monolithic transformer models while reducing the cost per batch by over 37%. And we've also shown here that the training strategy that we use for the Cascade Transformer is both stable and jointly produce smaller transformer models that are also suitable for ranking. Thank you very much for attending my presentation. If you have questions or comments, please do get in touch either via email or via Twitter.